All right. Good afternoon, everyone, and welcome to another Balerion Space Ventures podcast. Today, we are joined once again by Richard Dinan, founder and CEO of Pulsar Fusion. Pulsar is an advanced propulsion company that has spent more than 15 years developing high-power electric propulsion systems, culminating with fusion propulsion for space logistics and transport with Pulsar's Sunbird system. The fusion sector has incredible momentum right now. It is no longer viewed as speculative and distant. Real plants are now being built, but fusion is viewed almost entirely through the lens of terrestrial grid power. There is a compelling argument made by Richard that fusion propulsion in space may be a nearer term accomplishment. So, Richard, welcome back and thank you for joining us today.
Yeah, thanks for having me.
I think Pulsar has been in business 15 or 16 years now. And I
Yeah,
want,
yeah.
yeah, I kind of was wondering if we could, before we get into your latest work, which has been pretty significant over the last year, I was wondering if you could tell us kind of the story of Pulsar and how you first began.
Well, we began knowing that there would be a time when fusion propulsion would come, but we didn't know when. And also, I know that, I am very exuberant about fusion and passionate about it, but I know that many people have been before me, 50 years before me, extremely passionate and enthusiastic about it. And, that consistent ditto that it's always 30 years ago away and always will be. And so I thought, well, rather than just sort of challenge that narrative, let's assume that's true. What can we, rather than just being a company that raises money for fusion, big, heavy fusion prototypes? And I know that prototypes are prototypes for a reason that they probably won't be right first time. I didn't like the idea of these really expensive $100 million prototypes that probably were just a learning curve. And that was very healthy. And I didn't want to be perpetually raising money. I wanted to have a business. So we thought, with all the brilliant plasma physicists in the UK, what could we do to actually have a trade whilst developing this? And building large ion engines was a really good solution because it meant we could build these very big chambers. And it's ultimately about plasma under electromagnetic confinement anyway. So it's the right skill set. It meant I could employ these physicists, but more importantly, listen to clients, learn what they actually wanted. And if they don't want fusion propulsion, don't do it. If it's not, if it's a sort of how interesting, maybe one day, but we don't care. But then at least because we're talking to them about developing current systems. They tell us about our mission, their missions, and what they want to do in future. And what we found is that actually the appetite for really powerful propulsion systems is incredible and has never been stronger. So we have a business that builds these engines. We also build some power supply units and test them, these very big vacuum chambers. And now the Sunbird project, which is our fusion propulsion project, has never had more momentum and interest. And I think it'll fly.
Yeah, it's it's an interesting approach because as we've watched the momentum in the fusion sector, even in the best case scenarios for power, we're looking at commercial power really be scaling around 2040. And so a lot of companies you'll see will pivot to other things to have revenue in the meantime. Radioisotope generation or, some kind of tritium supplier, things like that. And your model, you almost anticipated that from the beginning and worked backwards and kind of took the baby steps first as the initial approach, it sounds like.
Yeah, well, I've seen some other companies who, typical university spinouts, the more traditional journey, they get university funding, and then a VC comes along, and a bigger VC comes along, and the valuation is really high too quickly. And then they build a prototype, and obviously it needs iterating, as prototypes do, and the investors can become impatient too early, and then those companies can lose value. And once those companies start losing value, it can be a very nasty journey, especially if you haven't got a revenue stream and when rates are where they are. And we didn't like the idea of trying to hold large valuations with no revenue. Also, pivoting, and again, not criticizing here, but if I spend 600 million on a reactor prototype and then pivot, that pivoting is good, but not if you're binning, that kind of hardware. And it needs to be done. Don't get me wrong. Fusion systems need to be developed, and it's fantastic. I just didn't want to be. I don't think I was the right person to raise private money to spend on that. Um, I think, in a way, things like the biggest reactors are well suited for multi-government funding. And that's where some really important lessons will be learned. And then, the smaller companies can come along and take it from there.
Yeah, and even in this initial the initial products that you were making, these are Hall effect thrusters for satellites, which is a common thing, but you found a niche in that that's a little different.
Yeah, so we decided to give the bigger ones because
Yeah.
our thesis is that if access to space gets cheaper, then the size of the engines will be people want to do more ambitious missions and more maneuverability in orbit.
Yeah.
But we found that this is unattractive because you need big vacuum chambers, a lot of hardware, and the qualification process can be hundreds and hundreds of hours, which is unattractive to a startup that wants to raise money and get going. And the smaller engines were more commoditized as well. Whereas people just didn't really want to build these big 5 kilowatt, 10 kilowatt Hall effect thrusters. But we thought because our mission is to build big chambers and we like problems in plasma physics, it suited us. And actually, that thesis has played out. Especially with things that you understand very well, the new appetite of fission in space means that if we can get small module fission into orbit, then suddenly the demand for these big ion engines grows dramatically. So it's been really exciting in terms of our work in coupling fission reactors to large Hall effect, because suddenly you've got the power and you can maneuver satellites. So that's been very promising.
Yeah. And because in addition to that, we're seeing in the satellite industry, the bigger satellites are already coming. I'm seeing kind of 10 and 20 kilowatt satellites now kind of becoming the next wave, which is right, I'm
Yes,
assuming, where you would become needed,
exactly.
right? And then the
But
second part of
they
that,
are sorry,
no, go ahead.
they are painful qualifications still. I mean, it can take you 10 years sometimes to qualify a large Hall effect thruster for deployment in somewhere like under ESS standards in Europe, because they're obviously very expensive satellites they're going
Yeah.
onto. And so, and you need, three by 5 meter chambers, if not bigger, to test these things. And they are very heavy investment, capital intensive project with all the cryogenics that are required and thrust balances, and none of this is simple. Um, and even burning sometimes millions of dollars of xenon fuel in qualification. So it's no mean feat, and it's important because I think when we talk about fusion for propulsion, I think if we're saying that we've never even built a product at all, then what I'm trying to say is that by doing this kind of work, it makes us less naive to the challenge of fusion propulsion is an incredibly ambitious endeavor, and I guess say that we know that, and we do understand exactly what that entails.
Yeah, and with what you said earlier, what do your facilities look like now? You're saying you would need really big facilities to test these and develop these products. So what's it look like in the UK now where you're operating?
So we've got two facilities, and they are predominantly now occupied by very large, and I say very large, to give you an idea, it's 3 meters wide by 5 meters length. It's like about the size of a railway carriage.
Yeah.
Um, Vacuum chambers, and we've got four of them. We've got two in service, one which is a qualification chamber. So you can actually have several Hall effect thrusts on each side of the chamber, and you can qualify. We want to be able to qualify 8, 16 Hall effect thrusters whilst maintaining a vacuum, because there's again, you have a yield on these things like any other product, but you have to deliver flight qualified hardware. And if you have to pump down a vacuum chamber every time you want to qualify an engine, it's going to take you a very long time to deliver to your clients. So MRL, manufacturing readiness levels, is really, really important, because a lot of companies haven't quite cracked that yet. There's a really big bottleneck, and it's not simple. It's really difficult.
Okay. And why is it that Hall effect thrusters and plasma, like how does that relate to progressing to doing fusion?
It doesn't. Other than the vacuum, being able to build and control large vacuum facilities, being
Okay.
able to you know confine a plasma within an electromagnetic field and analyze it is important. So things like,
Yeah.
setting up the probes in the right place, understanding how to measure thrust in a vacuum, which is, again, there are various ways of doing that accurately. But more importantly, when you talk about the fusion side, it's being able to give real data. Because if you can early on give primes or perhaps the government, if you can give them real figures, whether they be promising or not, that's what they want to see. And so being able to set that up properly has been really, we've learned a lot from qualifying large iron engines there. And again, no one has qualified a fusion propulsion system yet.
Right.
So there will be, it's not as if you can just take a Hall effect thruster out and put that in, but it is useful learning.
Yeah. And so before we even get into diffusion, you have paying customers. You've not needed to raise money yet. You have testing facilities. You kind of have all that foundation, it sounds like, in place.
Yeah, we have got some contracts from the European Space Agency and from the UK Space Agency. And the UK is a good place to do this because we can supply Europe, we can work with the US, and I think that's where the UK is suited. We shouldn't be competing to try and have our own launch facilities. It doesn't make any sense, in my opinion. Um, Again, in my opinion, but I do see we have a strength in plasma physics, and providing good stage two propulsion systems in partnership with the US is very suited to the UK. We have a lot of very good physicists here, and it's really what's lovely about Pulsar. Not just saying this as this is not a rehearsed line. It's just seeing these people employed doing what they're really good at in a brand new facility with the best possible equipment is really a great thing.
Okay. Yeah, that's cool. And I guess so then as you evolve from that and you got into fusion, kind of maybe a good way to get into that is that you were recently at an event with Jeff Bezos in the United
Yeah.
States, and you demonstrated kind of a thruster portion of your fusion propulsion system. Could you tell us
Well,
about
yeah.
that?
So what we're trying to do is the physics of fusion is very well understood, as you know. Um, but what we don't know is the exhaust architecture. And we want to build the piece that can ultimately, the component that can turn a fusion reaction into a thruster, because there are some questions that are being asked. And the first, if we want to build a propulsion system, is what temperature do we need to get to in terms of plasma to have useful thrust? Now, this is where a lot of people say, well, obviously, you've got to get to a level of efficiency. And if you're building a power station, you would. But if you don't care about efficiency and you only care about exhaust speeds, then you could be driving, you could do some inefficient things to sustain this plasma. Or one is you could have a fission reactor powering it. Now, that might sound very complicated, but we're already going to be putting fission reactors in space, and we're getting,
Right.
this is not an unusual thing to do. So we will have fission, and that gives us a lot of power to trigger these and to sort of run these kind of plasmas, and you can pulse them. But if you have, say, a temperature which gives you a reaction rate, say with helium-3 deuterium, maybe that's 20 keV or something. If your exhaust is not efficient, then that doesn't matter, because if it depends on how many ions you've got coming out the exhaust in the right direction. And if you've only got a couple and the rest are being, inefficiently spread around your reactor, then the temperature is going to move again. So before you get useful thrust from a fusion plasma. So what
Yeah.
we want to do is if to start with the exhaust architecture is, say, not very efficient, we know the test we did in California at the Amazon Mars event was not us saying we've cracked it. It's a first step of a plasma in the right place in your exhaust, so that you can start heating it up. And it's, because when we started doing this, you had arcs all over the place, you had plasma and building up in one area where you didn't want it. But you've got to be able to confine it in relatively the right place so that then you can start to turn up the temperature and you can start doing materials research. And that's where it's really getting interesting, is the material sciences going into this. And then we can give real numbers to whether it be DoD or primes, or we can say at this temperature with these fuel pairs, you get this thrust. And they can say, okay, well, that's a science experiment. Good luck. If you can
Right.
get to here, it's a DoD application. If you can get to here, it's commercial. And I see that there is a lot of room for improvement in the exhaust because it just hasn't been addressed properly. Fusion reactors are coming on a pace, but this exhaust problem it just hasn't been addressed. And so that first plasma, as you say, at the event hosted by Bezos, was really important for us. But it wasn't us saying, yeah, we've done it. It's just, now we're going to turn up the temperature.
Yeah, that's cool. That's interesting for two reasons. I mean, I'd say the first is, there's ways of tracking whether a fusion company is progressing, whether they're real or not, what they're doing. And there's a few metrics out there, but one of them is the Commonwealth Fusion Systems. Bob Mungard's got a list of, here's the steps you have to go through. And step number one is making a plasma. And it's actually not that many people that have done that, and Pulsar's done it. Um, that's one thing. And then the second thing is, I guess what I had not appreciated this before, but what it sounds like you're describing is that the exhaust portion of fusion propulsion is kind of like the power conversion for a fusion power plant. Like they'll make heat, let's say, if they're doing that form of conversion, and like if they make 3.5 megawatts of kind of thermal coming out, then maybe they get 1 megawatt from their whatever they use, turbine or something to make electricity. And I'm kind of hearing you say that maybe exhaust is like that too. You have a certain amount of energy available, but maybe it gets lost or wasted, and you're trying to capture it.
Exactly. So if you're using, say, a tritium deuterium plasma, which is what you'd use for fusion for energy, it
Yeah.
creates neutrons, and neutrons go everywhere. So there's no way any system can divert that out the back of a spacecraft. So it, in my view, is a useless fuel pair for propulsion.
Okay.
Could be
So
good
no
for
no
energy,
DT.
but
Okay.
yeah, but also DT is it's creating a lot of neutrons and a lot of radiation. You've got radiation to worry about anyway in space, and I don't want to put
Hmm.
expensive hardware in orbit, which is going to decay.
Yeah.
Um, I need my reactor to live a long time, because otherwise, if it doesn't, then you lose a lot of those gains. Because if I have to strap a new one to every spacecraft that launches, then actually I add fuel, I add weight, and I add costs. So it's, again, that level of useful escapes me. But if I can leave it in orbit and it can survive for time and it can do multiple transfers, then the numbers get really interesting. And we're seeing that with material studies that we're doing here with the Atomic Energy Authority that show that these systems will live in orbit. And it's really interesting. But you're right that it's the offtake. So if you've got, something like ITER, the International Thermonuclear Experimental Reactor in Provence, that is a 20-something billion-dollar fusion reactor, tokamak, but it doesn't have an offtake system. It doesn't have a steam turbine or anything to take. Its goal is to achieve Q10, I think, Q equals 10. So
Hmm.
it will achieve these neutrons and heat, nuclear heat, but it won't do anything with it. Therefore, no energy will come out of ITER. There is another reactor after that called Demonstration Power Station, or DEMO, and that will be the one that actually has an offtake. So yeah, it's that you create the plasma, and then you have to have another system to use that. And for energy, you also have to have lithium 6 around your neutrons, because neutrons hitting lithium 6 will ultimately create tritium, which is one of your original, it's the isotope that's actually less abundant than deuterium. So you need to be able to breed your own tritium as well in order to do this. And you can do that but as you say, it's from getting that plasma to a power station. It's a massive infrastructure project that on its own could take 20 years. For propulsion, if you say that, that the most practical fuel pair is helium-3 deuterium, and I know everybody is now saying, where do you get your helium-3? But we'll get to that. Then it's a higher temperature required before you get to peak reaction rate, which is somewhere near 50 kV, which is an awesomely high temperature if you were to use it for energy. But we're not using it for energy, and we don't need to. We can breed our own fuels off-site and buy them, bring them to to the spaceship. As we said, we can have a fission reactor driving that reaction. And we can even do tricks that you can inject things into your plasma to change the density of the exhaust. But the important thing about the protons is that protons are charged. They will feel electromagnetic fields, and you can divert a proportion of your ions generated in the nuclear reaction out the back of the spacecraft. And that will generate a specific impulse, which would dominate anything else, which is why there is such interest in it. But if, as you said, you've got, say you could hit 50 keV and you get peak reaction rate for deuterium helium-3, if your exhaust isn't very good, it's wasted. It doesn't matter. Or if your spaceship can't live, again, you might as well stick with Methalox. So you need to have a level of exhaust efficiency, as well as different missions will require different temperatures in order to justify the efficiency of them. And you also need to have the efficiency of the exhaust system, and it needs to survive. Sorry, I feel I'm waffling on a bit here too much.
No, that makes sense. And I think there's a lot in there that I think is worth highlighting because so the one thing is, I think people understand Q that for fusion power on Earth, you need to obviously get more energy ultimately than you put in, and or else you're not making power. And so Q measures that. Q equals 1 means you've reached parity. And I think I've heard for power stations, you're looking at like Q10 or 20 to really have a useful power station, which is very challenging, and that's what companies are working to do. But for space, as you've described, you don't need to become a power source right away. You're making a fusion engine, and that can be powered by something else. So like what do you have a sense of what kind of a Q you need to reach to have a useful power propulsion source?
Well, we can guess. I think let's say you invert this problem. If say I
Yeah,
was building a power station, if I
yeah,
said, right, we need to buy in mass amounts of really expensive helium-3, that would mean that actually you're better off stick with fossil fuels, or you're better off stick with solar.
yeah,
It's got to be better than that, significantly better. And it's got to produce more energy than is required to run the reactor. Otherwise, it is not a
right,
power station.
right,
Um, so conversely, on a propulsion system, if you only care about speed in space, and you say, right, I don't even care if I lose a lot of money doing this, because I want to be there. I want to have, say, I just want to have a dominant propulsion system. I want to have a really expensive, even inefficient system. But I can then say to the world, we as a nation have the fastest propulsion system up there in space. We strategically, if there's an opportunity in orbit, we can dominate that opportunity because we have this system, even if it costs us a fortune in breeding originally, and even if it's inefficient in the fact that we have to have fission reactors to drive it. So
right.
a useless power source. There is a point where a company isn't going to pay for that, but a government might. And so say we get to 20 keV in a plasma, which is where you start getting measurable reactions in deuterium helium-3, and we have a very efficient exhaust, then we can put those numbers to the powers that be, and they can say, not interesting until you get here. And companies might say, nowhere near interesting for us until it's significantly more efficient.
Yeah.
But we our first stop is to get to 20 keV, because I think that is where we can actually record, as I said, measurable thrust from a fusion plasma, which is what our mission is to do. Is the first
Okay.
stop is to demonstrate it, prove it.
That's like a triple product number that you're saying?
No, it's a temperature of plasma. So it's measured in keV. It's like just in I mean, I know you didn't know this, but just for people out there, it's like if you measure particles, the speed of the particles is actually heat.
Yeah.
And so that's how the temperature of plasma is measured. And 20 keV in plasma temperature is where you would start to see, it's not the peak reaction rate, but it's where you would start to see useful nuclear enough reactions for it to be measurable. But the peak reaction rate is around 50 keV, which is seriously high. That's almost twice what you'd need for deuterium tritium in a power station. But this is that doesn't mean you have to get there in order that if we could get there, then suddenly we'd have a propulsion system that could power itself and power
Hmm.
missions, and you wouldn't need any fission reactors. Um, maybe one day we can. Maybe one day we can do that. And if it's pulsed and it doesn't have to be held for long periods under confinement, and if your material science is good enough, there's no reason in space you can't do that. And finally, the really important thing to know is that, as you know, we don't have liquid methane in space. So as we what the world's, I think when we see things like Artemis, and that's wonderful, people start saying, well, we've just burnt a container ship worth of fuel to put this thing in orbit. And how, as much as we want to go to space, and this is wonderful, is this a really great thing to be putting all of this fuel, as much as we support NASA? Um, the reason being is because these spacecraft have to carry with them all the fuel for the whole mission and the return journey, and then the
Yeah.
fuel for that. And so there's massive amounts of rockets. And if you did have a system, not saying it's our system, but if you could launch your rocket, and then once you get into a different environment, you turn off your combustion engines, which are good for the atmosphere, and you switch to a propulsion system which is ideally suited for that environment, and it was there available to you, then you could save 90% of the fuel payload of Artemis, which saves a tremendous amount of liquid methane being burned in our atmosphere. It also saves a lot of costs. So you can see why you would pay huge amounts of money in terms of breeding helium or uh, putting these things up there in space in the first place, or having fission reactors drive them, because it's very obviously worth doing. Um, and then finally, space is the world of nuclear. Fusion happens in space. It naturally happens in space. It doesn't happen on Earth. So to do it on Earth is quite unnatural. You have to do a lot of tricks to even have a chance. It's very hard. But space is where we see fusion happening, and all the fuels for it are in space. So we're leaning into an environment where the fuels are available too. So in my mind, setting fire to things as a mode of transport in orbit is not something that we will do for long. I think we will get there, and suddenly we have not only the launch capacity. I say America has the ability to launch this kind of hardware, but we have the need and appetite too. So it's a very interesting cross section of capability and requirement.
Yeah, so it's like, why do I care about this, or why do we need this? And right now, like you mentioned the example of Artemis, we have to have our largest chemical rockets available, and it's all to take a very tiny and highly controlled amount of mass to get to the moon. And if you really want to start bringing things to the moon, you've got to have some other way to, you're going to have some other way to get stuff there, some other propulsion system.
Yeah, but also if you say, well, I mean, there are companies who want to build a space station around Mars, which is
Yeah,
wonderful, but I imagine they don't want to spend 15, 20 years doing it.
right,
I think if they want to deploy that asset, they want to actually be able to start getting a return on that asset within, if you can, as I've often said, speed in space is kind of fungible with money. If you
right.
have a fast propulsion system out there, you can grow the GDP of the whole space economy. But I do think that there's one day of this fusion propulsion being an efficient system that powers missions, and I do think that's there one day. But I think, what can you do today? Firstly, measure it properly, put real numbers on paper to find out where this box is of where we need to be. So we can say, right, at the top of this box is useful commercial um, transfer vehicles, and at the bottom is literally just really expensive DoD application only. And outside
Hmm.
of this box is a science experiment.
Yes.
But we need to be clear of where those metrics are. And to do that, you have to have a first plasma. You have to be able to start measuring that plasma in a way that is acceptable, like as we see ESS standards, at the right vacuum that's relevant for space qualification. And that's what we're trying to do today. And I do, looking at this problem, the potential for advancement in these exhaust systems is fantastic. And having we said the Atomic Energy Authority here, who are brilliant. They do the Jet Joint European Torus. They've been very responsible for the work in ITER. They've got the mast upgrade reactor. These these are, um, I think I can't speak for them, but changing their angle from looking at power to,
Well, let me ask you something that uh, based on what you said before, because I want to kind of push this controversial thesis and get it out there more because I think it's so cool and I think it's true. Why is fusion for space propulsion, maybe a nearer term or equally or better bet than fusion for terrestrial power? Like, I just think let's make our kind of case.
um, well, any kind of fusion, dependent on what conditions you can create in a plasma and what you can, if you can achieve a very high temperature in a plasma, but more importantly, confine it. Because as you know, the issue we have always had with these reactors is that they are unstable under very high temperature. And you only have a few things you can do about that. One is to study the cause of the instabilities with things like magnetohydrodynamics and fluid dynamics. And ultimately, you're dealing with a weather system that's a bit like chaos theory. So it's unpredictable by nature. And we aren't going to just fix that. So we have to learn tricks of how to better manage that plasma. But you can just up the magnetic field strength, which is why superconducting magnets have played such an interesting part. You can just basically add muscle, but then you get further away from your Q, as you said. So to answer the question simply, to produce a fusion power station that is going to rival solar and fossil fuels to an extent that it will replace them, they need to be at least Q equals 10, as you said, or better. And they need to be cheaper. And they need to be able to be, people don't want to have an ITER. So that's not a power station. That, demonstrations power stations, but still, they could be 50-year builds. They have been, or I mean, 20-year builds. Look at how long it took to build Hinkley Point C and how they have to fund them. So what I'm saying is, even if you could achieve your Q equals 10 plasma, you have to build the massive infrastructure of a power station around that. I don't know how technically you want to go into, but you need about a meter of steel around your reactions to slow the neutrons, to get the kinetic energy from the neutrons. Or you can use liquid walls, which is quite interesting as well, or salt water, liquid metal. But then you have to have your lithium-6 breeding belts around that. And then you'd have to have robots to maintain the system as it degrades under the neutrons. And then you need to have a steam turbine around that. And you might need to have another reactor so that one is on downtime and the other one can fire.
Yes.
And then you've got to protect your rare earth superconducting magnets from radiation and decay. So there's a point where this has all got to be better and more efficient than solar or fossil fuels. Otherwise, it won't take over. Whereas if you can produce that same plasma condition and launch it, which is something that we can do now, you don't need to breed your own fuels. You don't need to slow neutrons. You don't need to have a steam turbine or have any kind of. You can literally waste a lot of that nuclear heat because all you care about is exhaust speed to start with, is that specific
Yeah.
impulse,
Yeah.
and it is such at about 13,000 seconds of specific impulse. And then ultimately you will be able to tinker with the thrust as we get better at it. And there's about 10 newtons of thrust from a megawatt of fusion, roughly. There's equations out there, again, depending on the efficiency of your exhaust. But none of that infrastructure, heavy, long-term infrastructure, is required for propulsion. And so you might have a 20-year advantage over two people that can achieve the same conditions in plasma.
Right. It's
That's
it's
my
crazy to say it. But it's true. The fusion propulsion, it's a simpler engineering project than these plants on Earth. And then the second part that you said, the competitors. I mean, there's so many energy competitors on Earth. I mean, I think fission is fantastic. That if we do a lot of that, you can do a lot of that on Earth, and very hard to compete with that. But in space, we haven't made it explicit, but there is some competition. You have chemical rockets, you have Hall effect thrusters and things like that that you make, and you have nuclear thermal propulsion, and you have fusion propulsion. And, can anybody compete with fusion propulsion? What's the advantage?
Um, I'm sure you've seen the figures, but
Yeah.
doesn't it? It's you know it the numbers are enough to justify launching a fleet of fusion propulsion tugs and having them maintained in orbit. Um, the numbers are there to justify doing it.
I know it's speculative. Look at, like I was kind of asking about a Q for propulsion. It's kind of the same thing, but what, roughly speaking, do you have kind of a days to the moon, days to Mars type of number?
Well, if you look at things like, I think calculations done by people like Princeton Plasma Physics Laboratory, I think they halve the time to Mars. But there are a lot of unanswered questions: deceleration, launch, the again exhaust efficiency. I don't know what temperature they're assuming. Maybe they're assuming peak reaction rate. Maybe I don't know if they're assuming it's being driven by a fission reactor.
Yeah.
And I think one of the problems is we don't have real numbers. Um, we need to know where that box is in terms of efficiency reaction rate
That kind of goes to your
before
original
we
point of
can.
why that actually in itself is a product that can kind of provide early on, that kind of beginning to gather that knowledge.
Yeah, because then you can say, right, well, this is where we need to be in terms of plasma temperature and exhaust efficiency in order to please this client. Um, and for maybe bigger missions, we do need to be at higher temperatures. Maybe there are different mission profiles where you can pulse. Maybe you can, as we said, you can inject impurities into the plasma to increase and sort of throttle these things. It doesn't give you um, the same specific impulse, but it can give you thrust where you might want thrust. So I'm not trying to not give you a straight answer, but I don't, roughly, if you've got a perfect field reverse confinement system, you could halve mission times to Mars. Um, but I think it doesn't take into account how much you can reduce the infrastructure of the launch payload
Yeah.
and the weight of the launch payload. And you can charge a lot of money for that.
Yeah, and it's
Um,
fair to say qualitatively, with the two things you care about are thrust and specific impulse, how efficient you are. And fusion propulsion has the best of both of those, really. If you were to compare to, like, chemical, great thrust, bad specific impulse, the Hall effect thrusters, great specific impulse, bad, not great thrust. Nuclear thermal propulsion gets a little better, but fusion, it was really kind of the best of all, if I understand correctly.
Yeah, it doesn't give you that. You never get the thrust of a metal oxidation out of it.
No.
Well, theoretically, if you had, you know, gigawatt fusion reactors on the moon or
Yeah.
something, then it may be. But I think for what we're talking about, you will get tens of newtons of thrust, but you will have an absolutely dominating specific impulse. Um, and the two of them make a system that is unmatchable
Okay.
by a long way, which is why there's such interest in it. The other thing I would touch on, I don't know how much you guys are interested in this, but material sciences in these systems can be the difference between, as I said, if it's a one mission system, much less interesting. But things like lithium hydride for shielding, maybe not tungsten. Multi-layer shielding is very, very interesting. Um, Rebco magnets can survive with acceptable damage thresholds. So you don't want to build a spacecraft that lives longer than the reactor, but it has to live as long as the reactor. You want to build a rock that can just withstand this simple system with as little that can go wrong and as easy. You don't want robots maintaining this because that adds another layer of complexity. But the simulation shows that these uh, these systems will survive a long time in orbit, which is really interesting because suddenly that it gives you a lot more room if you can do several transfers before a system has to be deorbited or decommissioned.
Right, like that's what happened with launch, where it was so expensive because it was an expendable system every time, and
Yeah.
then once it became reusable, the price tanked, and so I guess so reusable in space propulsion like you'd be providing makes a lot of sense.
Yeah, and the other thing is that I mean, some of the research shows that these heat loads are manageable. and you can actually protect your superconductors from the heat. And this is physics that it's taking understood models that we use for energy and calculations for reactors and applying them. And it's not us applying them at Pulsar; it's people like the Atomic Energy Authority doing this for us. And it's amazing how a lot of the issues you have on Earth aren't an obstacle. There are other challenges, but some of this data is, I guess, we have it there. It's protected, but it's really interesting. It's very exciting.
Yeah, and that's, I mean, maybe it's a small point, but just we're going through the advantages, simpler engineering. It's not as many as really significant competitors, if any. And the third thing is, yeah, I mean, on Earth, you have to make a vacuum, right? And that's a technical thing in itself, and in space, you have a vacuum.
Well, if you look at the majority capex of fusion um, energy companies, it's vacuum chambers. It's very
Yeah.
big, very
Okay.
expensive vacuum chambers. We don't
Interesting.
need that. Your space is the perfect facility for that, as you said. It's just nature is on your side if you're doing fusion in
Yeah.
space rather than working against you.
Right. So what is next for Pulsar then? I mean, it looks like incredible technology. So you've already got these initial propulsion systems, these larger Hall effect thrusters that aren't as available on the market and at a time when they're needed. And now you're moving into the Sunbird fusion propulsion system. So what's Pulsar in 2035 look like?
Well, over the next 18 months, it's about setting up all the probes and analysis around these systems so that we can start putting those numbers in front of the people that can use them, and get feedback. And also, without getting into the commercials of it, um, these are the people who really do want to look at the system. They want to see these numbers too, to quantify their what they can use this system for and when. Um, so ultimately, turning up the temperature now. So we've done a first plasma. We've got some really exciting material sciences collaborations that we're about to announce. Some magnetics as well, and we'll just turn up the temperature. And we don't have to uh, do a lot of the confinement milestones that were needed for energy. We can just start working out where we find our problems, if it's at and how high we can go without where the next obstacles are. So it's about raising the temperature, but then ultimately, it's we want to fly. Pulsar exists to fly hardware. So there are a few companies in the world that can actually put this in space, and most of them are aware of what we're doing. And so long as the numbers, the forecasted numbers are happening in the lab, then I suspect this will fly. And I hope it does. And our ambitious plans are to have some of these systems doing in orbit demonstrations in 2030. So that's what we want to do.
Wow. And do you work through the steps again? And has anybody ever done a first plasma in orbit?
Well, we do plasma all the time in orbit in ion engines, but
Well, of course, yeah, that's right. Okay.
no one has ever produced a neutrons from a fusion
Right.
plasma
Right.
or recorded fusion reactions in space. But we would like to be the company to do so.
Okay, that's great. So you're going to do that. You're going to start with deuterium helium-3. And do you have to make new
Well,
facilities? Oh, good. Yeah.
no, we'd probably just start with anitronic research and things like just helium, because
Okay.
you don't want to start writing off your prototypes.
Okay.
Um, so a lot of times just do helium research to get the temperature up and to master the confinement, before you start putting reactive fuel pairs in. Um, but when you put the reactive fuel pairs in, you want to be sure that your system is working the way you want it. And we do that with under the supervision of the people who have the means to fly it.
Okay. And is heavy launch like Starship critical to any of this kind of eventually becoming fully successful?
Critical, yeah. The reason this is where we are, there's such interest now, is I think, look at China, they are very good at fusion.
Hmm.
But America has the ability to launch this stuff. um,
Yeah.
And that's why, to maximize that advantage, what you launch, you want to be able to demonstrate, propulsion systems that are unmatched.
Okay. And so you'll gather this data, hopefully you start demonstrating it in space, and then kind of the North Star, is this like a rail network to the moon and Mars?
The North Star is lighter rockets. So more you reduce the size of the original rocket as much as possible. The rockets just have to get themselves out of the Earth's atmosphere and into low Earth or mid Earth orbit, and then they will pivot to a propulsion system that is much more suited to that environment. If they're going to remain in low Earth orbit, then fission and high power ion is kind of ideal for satellites. But if you're talking about cislunar or cis-Martian development, then you need something with a fusion is the only system that gives you the numbers that would really, as I say, grow that economy in the way that we'd want it to. We don't want to be waiting 20, 30 years to build space stations. And the temperatures in plasma that we're already able to achieve as humanity on Earth already create a propulsion system which is absolutely, in a different class to anything else that's been tested in space so far.
Right. So I mean, I guess I'm hearing you say this is kind of an enabling technology because if you have this allows you to really, like you said, you can't take 2 decades to build a station on Mars or something. So this allows that to happen in an
It's
appropriate,
the only thing that allows that to happen, and
the only thing.
right, you can halve those development times and actually start monetizing your asset
Right.
in 5 years rather than 15.
Right. Well, it's a pretty powerful argument for why fusion, can be done in space and it's maybe a better approach in a lot of ways, and why this is absolutely critical for the space economy going forward.
But so,
Well, Richard, this has been very interesting. Is there anything else you'd like to leave with everybody before we finish up?
no, I just say thank you for your time and your your paper, Doug, you wrote was really, I think, one of the best out there. So if anyone hasn't read that, I'd give that a read. But thanks for having me on.
Well, thank you too. Thanks for being here. Always great to talk to you and watch Pulsar. Let's talk
Thank
to you
you.
again. Thanks, Richard.
Bye.